this will be a relatively short video. It's called Orbital Diagrams. It's kind of a continuation of the last video on electron configuration. And as we go through this, we're going to review the last video really quickly, but orbital diagrams are simply a more visual way to show electron configuration. And I think some of you will actually like these a little bit better. I think you'll find that they're even a little clearer on what we're meaning by electron configuration. But to review very quickly, first of all, there was the diagonal rule for figuring out electron configuration. All you do, you sit here, first of all, you write on your paper, you write 1s at the top, you write 2s, 3s, 4s, 5s, 6s, 7s. Right next to the 2s, you write 2p. Then you go down from there, right next to the 3p, you write 3d, down from there, 4d, put the 4f next to it, go down from there. That's all you need to do. Okay, so we're going to just go through a very quick review example. Neon. Neon has 10 electrons. Okay, we know that because it has 10 protons. In the neutral form, it has 10 electrons. Usually neon is neutral, so that's an easy thing to remember there. And so all we use is this little chart here, and we say, okay, the 1s sublevel gets filled first. We know that it has only one orbital, therefore it holds 2 electrons. So 1s, 2. Then the 2s gets filled second, that has one orbital, fills 2 electrons. So we've already accounted for 4 electrons. We keep going, though, because we have to get to 10. After the 2s, then we come back here. You see how as you get to the end of the arrow, you got to go back to the top, end of the arrow, go back to the top. Then the 2p fills next. And 2p holds, of course, it has 3 different orbitals. And so it holds up to 6 electrons. And luckily, we're up to 2, 4, 10. We have now 10 electrons accounted for. So here is the electron configuration for neon. So not too bad there. Now, I mentioned that the better way to do this, even though that diagonal rule seems so simple, you're going to find that it's actually more helpful to just be looking at a periodic table. And all you do is you divide up the periodic table into an S block over here, a D block right in the middle, and a P block over here on the right, and finally an F block down here. So you just take your periodic table. If this was your periodic table, you can even go on here and write that this is the S block, this is the P block, and notice I'm carefully leaving out helium, because helium really should be right over here when we're using this method. And then in the middle here, this is called the D block. And then down here is the F block. Okay, so as we're going through this then, let's just take an example of chlorine, the 17th element there. It has 17 protons, and therefore in its neutral form it has 17 electrons. And so all we do is first of all, we could circle chlorine there, but then when we look at where those electrons go, we start by looking at hydrogen here, okay, and we look at what block it's in. And hydrogen has a little 1 next to it, okay? So we can think about it as the first electron on chlorine, you can look where the 1 is here on hydrogen, fills wherever this first element is sitting. Now, you might wonder, why are we looking at hydrogen when we're trying to figure out the electron configuration of chlorine? I know that sounds confusing, but stick with me. You're going to see how simple this is in a second, okay? The reason we are looking at hydrogen is because the same place that hydrogen's last electron filled is the place that chlorine's first electron filled, okay? Because hydrogen, of course, only has 1 electron. Okay, so here's how we do it. So the first 2 electrons, this one and this one, think about, as I look at hydrogen, think about the first electron that's being filled. And as I look at helium, think about that as the second electron being filled. Both of these are in the S block, okay? And it just happens that this first row is the 1s row. This would be the 2s, this would be the 3s, 4s, and so on, okay? So in the 1s, we have 2. We have 2 boxes within that 1s block, so it's 1s, 2. Then we go to the third. See, now we're on number 3 here. Okay, so in other words, the third electron of chlorine fills in the same place as the last electron in lithium. Okay, so the third electron is in the 2s sublevel, which is over here in this S block, and as well as the next electron. So we've got 2s, 2. We've got the third and fourth electrons go into the 2s suborbital, okay, or the sublevel. Now we go on to the 2p sublevel, and we've got 1, 2, 3, 4, 5, 6. We've got 6 electrons. Numbers 5, 6, 7, 8, 9, 10 all go into, this is all the p blocks. So we've got 2p, 6, and then next, the 11th and 12th electrons, now we're on to the 3s. They go into, so 3s, 2, okay? And then we just keep counting. Now we're on to 3p. We've got 1, 2, 3, 4, 5. 3p, 5. All right, and that's all we need to do. That is the electron configuration of chlorine. Now, again, trust me, this will be your easiest method. I really recommend that with the diagonal method, maybe you use it at first, but use this one in the long run. It's actually quite simple, and you'll find that you can work it pretty quickly just by looking at your periodic table. You don't need to draw that little diagonal chart out, and it will also give you greater insight to why the periodic table is arranged the way it is. Now, on to orbital diagrams. Okay, there are 3 key rules for orbital diagrams. The first one, now some of these have funny names, but the principle is pretty simple. The Aufbau principle. The Aufbau principle is the lowest energy orbital fills first. I'm going to cross this out and put orbital. That will be a better word to use. And you'll notice as we're going through the terms orbital, sublevel, and energy level, sometimes we use those a little bit interchangeably, but the concept underneath, you want to get it very clear on what we're talking about. So don't get too caught up in exactly which word is being used. Look more at the fact, for example, that there are two, in the 2p sublevel, there are 3 orbitals, okay? And whether you call that the 2p orbitals or the 2p sublevel, the concept is the same. You're going to get 6 electrons in those orbitals, and that's what you want to be aware of. But the key here with the Aufbau principle is the lowest energy orbital fills first. We already know that from doing some of the electron configuration that we've done previously. The 1s orbital fills before the 2s, which fills before the 2p, which fills before the 3s. As you know, that pattern goes through. Hund's rule, this is a new one that you haven't learned yet. But not a very difficult one. If more than one orbital has the exact same energy, you put 1 electron in each before doubling them up. Okay, so a good example of this is the 2p sublevel. Okay, the 2p sublevel has 3 orbitals. All 3 of those orbitals are the exact same energy. Okay, and so when the electron is trying to decide which orbital to fill in, it wants to fill only one of those orbitals, 1 electron in each orbital first before doubling up. Okay. Another way to look at this, you could call this the city bus rule. As you know, on a city bus, nobody doubles up until there's 1 person in each pair of seats. Okay. And then once there's 1 person in each pair of seats, then people finally start doubling up. So you could call the Hund's rule the city bus rule, and that would be a good kind of way to remember that that nobody doubles up until 1 electron is in each orbital first. Okay, the final principle is the Pauli exclusion principle. And the Pauli exclusion principle essentially says something that you're already aware of, that each orbital can hold only 2 electrons. Okay? And here's the key here, is that each has an opposite spin from the other. Okay? So you can think of it as if 1 electron is spinning upward, the other electron is spinning downward. Okay, sometimes they describe that as a positive spin and a negative spin. That's a good way to discuss it. The only thing I'm concerned about that terminology is that when we say a positive spin, I don't want you to have the wrong impression that those electrons might have a positive charge. All electrons have a negative charge. Okay, so the charge is negative, but we're going to say some spin upward and some spin downward. Okay, and that's what I'll try to stick to in order to just keep that clear so nobody gets confused. Again, when it comes to charge, electrons only have negative charges. Okay, so now here's an example of an orbital diagram. Okay, I've got 3 different atoms here, and I'm going to just tell you a few features of these orbital diagrams. First of all, you'll see that you orient these vertically with the 1s down here at the bottom. Okay, that's because the 1s has the lowest energy. So as we go upward, we have increasing energy. Okay, so as you know from the Aufbau principle, the first electrons are always going to fill the lowest energy level first. And this is a good way to think about that, is if you're trying to load bowling balls onto shelves, you of course are going to fill the lowest shelf first before you go to the next level of shelf. So you can see these electrons. Now, the electrons in this diagram are shown by these little arrows. Okay, so an upward arrow is an upward spin electron, and a downward arrow is a downward spin electron. Okay, so each orbital has 2 electrons in it, and you fill them from the bottom up, just like bowling balls on a shelf. Now, one other thing to note here is you'll see these little horizontal lines. The horizontal line at the bottom of that circle there. The horizontal line represents an orbital. Okay, so in the 2p sublevel, you have 3 orbitals. Okay, here's another example of one of the horizontal lines. Okay, and that was something you're already aware of. You already knew that the 2p sublevel has 3 orbitals. And now you're just showing a visual representation of that concept by putting 3 little dashed lines. Okay, now let me go and show you an example of how to draw an orbital diagram. And I'm just going to give one example, but then we're going to give you some practice. It's something that if you practice it probably on about 10 problems, once you do 10 problems, you'll have it down. You'll have no problem. Easy to do it. Okay. So first of all, for the element of phosphorus here, let's look where phosphorus is on our periodic table. It's number 15. Okay. So we have 15 electrons to account for. Okay. Now, one thing you can do is just when you start, you could actually do this. You could have some blank pieces of paper that show your possible orbitals that could be filled depending on how many electrons you have. You always start down here with the 1s, then you go to the 2s, then you go to the 2p, you've got 3 orbitals in the 2p, and then you go to the 3s, you've got 1 there, and then you go to the 3p, you've got 1, 2, 3 there. Here's where it's a little bit funny. You go to the 4s next, and then you go to the 3d. 3d has 1, 2, 3, 4, 5. I know you're saying, why would we have the 3d after the 4s? So that has to do with the quantum mechanics of this. The 4s, for some reason, has a slightly lower energy level than the 3d, so it fills first. Okay, and there's some quirky exceptions in there, but when you look at the periodic table, you'll see that very clearly, and I can show you where you would notice that, so you never forget that the 4s fills first. But as I mentioned, I could just draw these blank orbitals, and then I could start filling electrons. Now, I'm not going to use all of these orbitals. I didn't need to draw all of these for the case of phosphorus because we're only going to make it up to, I think, the 3p. Okay, but here's how you want to fill these, okay? You want to put an upward, oops, sorry, I keep on hitting my button there. You want to put an upward arrow first, and then you put a downward arrow, okay? Now, I always do these little half arrows like you see here. It's like this instead of like this. I don't know, it doesn't really matter how you do it. These just seem to be easier to draw for me, but you can do it either way. It doesn't really matter. Okay, next you put a little upward arrow here and a downward arrow here. Now here's the key. When you get to the 2p, remember, because of the Hund's rule, this is the city bus rule, you only fill 1 electron in each first. So fill the upward spin electrons first, and then once all of those are filled, in all 3 of those exact same energy orbitals, then you fill the downward arrows next. Okay, this is important because this is how they actually fill. Okay, now we're on to the 3s. That's an easy one, up and down. And now the 3p, oh, we got to be careful because look, they're the exact same energy level. And so we've got 1, 2, and 3. Okay, and so that would be, and this is all we need. We wouldn't even need, we can cross these out. We don't need these orbitals. They're not being filled in the ground state of phosphorus. Okay, so here would be the orbital diagram for phosphorus. Okay, and now I'm going to give you some practice problems to work on, and as you work on those, I think you'll find this will come together pretty quickly, and you'll find this to be a relatively simple thing to do, and probably even more helpful because of the visual aspect than the way we did electron configuration previously. The reality is, we're going to do both methods. We'll probably use the standard way to do electron configuration more often, and then we'll use the orbital diagrams sometimes, especially when we're emphasizing things like the Hund's rule, where only one electron fills in an orbital before doubling up. Again, that's the public bus rule. Okay, thanks a bunch, and come in with any questions on these concepts.